Hi everyone, I'm Yu. Today I will introduce our paper, StingySketch, a sketch framework for accurate and fast frequency estimation. Nowadays, data stream analysis is becoming increasingly important. For a data stream consisting of many items, one may want to ask that whether a given item has appeared in the data stream and what the frequency of the flow is. For example, in this slide, as the yellow, gray, and yellow items come, their frequencies turn to 3, 2, and 4, respectively. Due to the high velocity and large volume of the data stream, we have to admit that it is difficult to record the whole data stream totally accurately. So frequency estimation is not to accurately, but to approximately measure the occurrences of items in a large volume and ultra-fast data stream. And the most promising solution is called Sketch, which is a kind of hash-based probabilistic data structure in recent years. Many applications, including finding top K items, drawing tables, multi-site querying, and net cache, use or even rely on frequency estimation algorithms. A typical sketch, namely count-min sketch, is composed of several counter arrays and hash functions. For each incoming item, like the yellow one, the count-min sketch randomly picks one counter per array and increases all of them by 1. Note that since the counters are selected by hash functions, when other items, like the blue one, comes, some counters may collide and their values may get larger. We call this phenomenon as overestimation. To alleviate overestimation problems when querying frequency, count-min sketch reports the mean value of all mapped counters to minimize error. In the left figure, for example, we recognize the 3 mapped counters are 2, 1, and 2, respectively. So count-min sketch report 1 as a result. Count-min sketch is a milestone whereby most existing works are observations of it. In some scenarios, sketches are designed to achieve high throughput at cost of accuracy, like augment and pyramid. While in some other scenarios, sketches would rather cost time in exchange for accuracy or compact space, like SAC and SALSA. We regard these two kinds as speed-oriented works and accuracy-oriented works, respectively. Based on this taxonomy, we find that no existing work can achieve both high speed and high accuracy simultaneously. And this is what our work strives for. Our motivation is to use a hierarchical data structure to allocate appropriate counter size for different flows. To be more specific, we expect to use small counters to count mice flows and to allocate large counters for elephant flows. This thought is based on a widely acknowledged hypothesis that many data streams obey a highly skewed distribution. That is, a couple of elephant flows appear thousands of times, while most flows are mice flows, which only appear a couple of times. Therefore, compared with a flattened array with fixed size counters, dynamic counter size can save much memory and thus reduce error. Okay, so much for the background and motivation. Now let's talk about StingySketch. As I once said, StingySketch is a hierarchical data structure which splits an int or integer into 8 4-bit parts. So in this picture, Every small counter, no matter blue or gray, is a counting unit. Blue counters and green counters locate next to each other. Now, here comes a hierarchical structure. We call it bit paging counter tree, BC tree for short. Although green and blue counters physically locate near, they are in different logical levels. A blue counter belongs to a 0 level, whereas a green counter belongs to a non-zero level. It is these different levels that help StingySketch to dynamically allocate variable-sized counters. To be more specific, when a new item comes, StingySketch maps the item to a blue counter and updates it. At this time, the flow only occupies a small 4-bit blue counter. When it is full, however, the blue counter may carry to a green counter of level 1 according to the arrows in the figure. So the flow occupies 8 bits memory to count its value. If the green counter overflows at will, it may carry to a 2-level green counter, and the flow will take 12 bits. In this way, the memory can be dynamically allocated as long as we can recognize how many units a flow takes. But how to recognize the counter size? We can easily solve this problem by designing the state transition model of each unit counter. To be honest, it's quite similar to a normal counting process. I mean, we have 16 states. State 0 is followed by state 1. 1 is followed by 2. And 14 is followed by 15. The only difference is that in our design, the successor of state 15 is state 1 rather than 0. In other words, once the counter is mapped, it won't turn to state 0 any longer. In this way, a 4-bit counter has 15 rather than 16 valid states to count. But we can determine how many units the flow takes. For better understanding of this design, next we give 3 examples. The first example is very easy. Here is a new item, the red E, comes to an empty blue counter. It simply updates the blue counter from state 0 to state 1. When we query the flow, we locate the blue counter and its parent node. Then we find the parent node is 0, so the flow only takes 4 bits. As a result, StingySketch reports 1 as its estimated value. The second example is that an item coming to a blue counter in state 15. Based off state transition model in the right figure, it updates the blue counter from state 15 to state 1 and overflows to its parent node. When we query the flow, we find the grandparent node is 0, so the flow takes 8 bits. As a result, StingySketch reports 16 as its estimated value. Now, we give a more complex example. That is, the flow may collide with other flows. Look at this figure. StingySketch updates the blue counter from state 15 to state 1 and overflows to its parent node. Similarly, the parent node overflows and turns to state 1 as well. But on the other hand, after the grandparent node turns state 1, the red flow collides with the blue flow, which makes the estimated value wrong. In fact, the problem is not that severe because we can use multiple arrays and report a minimal value to reduce collision error. In our paper, we provide some tricks to avoid high-level collision, but these tricks are time-consuming. In the remaining time, I'd like to introduce another two techniques to accelerate the processing speed. The first one is profit queue. It is similar to batch processing technique to some extent that makes the hashing process and addressing process in parallel to shorten the critical path. Let's review a typical insertion. Given an item, we first compute its hash value and get its counter's address, then take the address from memory to catch and register, and eventually update the counter. During the process, other items have to wait until we finish updating the current item, which decreases the processing speed. Now, we suppose a queue structure, namely profit queue, PQ for short, to solve this problem. Given an item, we use prefetch technique to take its address and put it into PQ. But we don't really update the counter immediately. Instead, we process other items until the counter is fetched into cache. In this way, no items will wait, so the overall throughput is much higher. The last one technique is bounded hash split. As I said, Sketch uses several counter arrays to reduce error. If there are L counters per array, it seems that we need D times log L hash base to map the counter into D different counters, to map the item into D different counters. Bounded hash split is a technique to reduce this hash computation overhead without losing much accuracy. To be more specific, hash split use one index part and D offset parts to find the D different counters. In this example, the index hash value is 2, and the offset parts are 6, 4, and 2 respectively. So the target counters are the 8th counter in the first array, the 6th counter in the second array, and the 4th counter in the third array. In this way, we need only log L plus D minus 1 times alphabet hash bits to locate all the counters. And in our paper, we have proved this method only causes a small accuracy drop. In other words, its accuracy overhead has a theoretical bound. Here we show some experimental results measuring accuracy and speed on 4 kinds of datasets. We find that StingySketch is up to 50% more accurate than the SOTA of accuracy-oriented sketch SALSA, and it's up to 33% faster than the SOTA of speed-oriented work Pyramid. So in conclusion, today we have talked about StingySketch. It uses hierarchical BC tree to increase accuracy and uses profit queue and bounded hash split to optimize processing speed. We hope these techniques can be used in many other domains. Thank you. Thank you for your listening.